With understanding of numbers, strings, and tuple, we can now create new compound data for use in applications. So we will see an example of a rational number in this video. Before going into the detail of implementing our rational number, first we see some guidelines for creating compound data and their associated functions. We need this to help us understand what are needed so that whatever created new can be of some use. First, it of course must have constructor so that such a compound data can be created. The creation could be directly from primitive data, and it can also be from other ADT or compound data. Then we need function means to access or modify each individual component, since this is a compound data and we need not know about the compositions, how each component is made of. These are called the accessors for accessing the data component or mutators for modifying the component. Also, it is common to have checking to see whether an object or data is indeed this compound data. Checking of this should be provided by the compound data since it knows itself the best. Of course, we need ways to display the compound data in a human readable form. One possible use of this is for debugging. Of course, very often applications also need to know what is actually this compound data in a readable form. Then, having such compound data, we want to know ways of working or operating with the data without knowing their internal representations. Our example of rational number has most of this except that it doesn't have the mutators. A rational number is a number that can be written as n over d, a fraction, where n and d are integers. N is called the numerator and d is called denominator. Since a rational number can be viewed as two integers, it is natural then to use a tuple with two elements to represent it. Of course, this is just one way of doing so. We will show you another way later on. So the constructor will look like this with a tuple to represent a rational number, nd, with input of n as numerator and d as denominator. So define make underscore red rational number, input with n and d, you return a tuple n comma d. So with this constructor, we next see the selectors or the accessors. So given a rational number, to get its numerator, we simply return the first element of the tuple. To get its denominator, we simply return its second element of the tuple. It is easy to check whether two rational numbers, x1, x2, are equal by taking the cross multiplication of their numerator with the denominator. Numerator with the denominator. They are equal if and only if n1d2 is the same as n2d1. So this is numerator of x1 times denominator of x2 is the same as numerator of x2 times denominator of x1. Also, it is easy to check whether a particular input is indeed a rational number by first checking the input is indeed a tuple, the length of the tuple is 2, and the numerator is an integer and the denominator is an integer. So this is the complete checking. You can check for yourself that this checking of tuple is needed because this method numerator requires it to be a tuple. Same for the denominator. Then, to print out the rational number, print red given the rational number, we first ask for the numerator, make it as a string, concatenate it with slash, and then ask for the denominator and make it a string to print it out. Now, notice that we do not use red 0 directly, even though numerator red is simply red 0. This is no good because in the event that the rational number is not represented as tuple anymore, then this function will not work. On the other hand, this version will survive with the change of any new representation of the rational number, as you will see later in this video. Next, working or operating with rational numbers. To add two rational numbers, here's the math. First rational number, second rational number. The new rational number, it's just simply the multiplication of their numerator and denominator. Numerator and denominator divided by the product of the denominators. This translates directly to Python as taking out the numerator and denominator of the first number and the numerator and denominator of the second number, making a new rational number for output with the numerator according to the formula here and denominator according to the formula here, and you are done. Similar to the addition, subtraction is simply having a minus here, which translates to a minus here for the numerator. So the function sub_ret is simply returning, making a new rational number with the numerator according to the formula here with the minus sign, and then the denominator as the product of the two denominators. Here is multiplications of two rational numbers, x1, x2, and the formula is simply taking the products of their numerators over products of their denominators. So multiplication is to return a new rational number with numerator equal to this and denominator equal to this. It is clear division is to make a new rational number according to this formula, numerator of x1 times denominator of x2 as the numerator, and denominator of x1 times numerator of x2 as the denominator. Here are some examples on how things are like when working with the rational number. We define 1/2 equal to make rational number 1 over 2. You can check, is 1/2 a rational number? Yes, it is a rational number. When you print the rational number 1/2, you will get 1/2. When you define 1/3 equal to make rational number 1 over 3, when you print it, you get 1 over 3. When you print the addition of two rational numbers 1/2 with 1/3, you get 5 over 6. Likewise, when you print the product of 1/2 and 1/3, you get 1/6. And you subtract 1/2, 1/3, you get 1/6. When you add 1/3 with 1/3, you get 6 over 9. Oops, this is not what we really wanted. We would prefer 2/3 instead of 6 over 9. So how? We need to go back to our constructor of rational number to fix this problem. In particular, we see that the GCD of 6 and 9 is actually 3. And so both 6 and 9 should be divided by 3 first before forming the rational number as 2 over 3. So here it is. The original make rational number simply take the number input as the tuple as output. But in the new version, we need to first calculate the GCD of n and d to get g, and both n and d must be divided by g before making the tuple as the rational number. Now you redo the exercise with this new make rational number. When you print add the rational number 1/3 with 1/3, you indeed would get 2/3 instead of 6 over 9. To sum up the discussion so far, this is an interesting and important slide. This is exactly the pictures of how software are built on top of each other, that is, layer by layer. For here we see the case of our rational number built on top of the tuple, but you should see this just as an example, and many other software are done in the same way actually. The reason to do so is once again helping us to manage complexity. Let's look at it layer by layer. In the bottommost layer, you have the tuple implemented in systems. So tuple is a primitive data type. So tuple provides this layer, and there are interfaces that can support whatever you wanted to build. Our rational number uses tuple as a representation. And we have make ret, numer, demo is ret. Make ret is to create rational number. Numer and demo are to get us the numerator and denominator of the rational number. Is ret is to check whether an input is a rational number. All these four functions know that the underlying representation is a tuple, and it can access to tuple whatever tuple can provide. And then this layer presents a rational number as numerators and denominators to support checking of equality of rational number, addition of rational number, subtraction of rational number, and printing of rational number. This third layer, access to rational number in the second layer, it doesn't need to know that rational number is actually represented as a tuple. So it doesn't access in this particular manner to the tuple. Now we have a complete set of functions to support operation with rational numbers. Programs that use rational number can then access to this third layer and this second layer. And this program doesn't need to know also that rational number is represented as tuple. So to recap, there are layers in the whole system. The layers are abstraction barriers. So this layer support this layer support this. Both these two layers support the programs. How each layer is to access the other is through contracts or interface without violating the barrier. This is a kind of interface provided to the next layer. This is another interface, this is another interface. So as long as you use all these names, equal ret, add ret, subtract, and print ret in this particular layer to support the next layer. All in all, such organizations of software is to help us in our management of complex systems. And in fact, it allows us to change a particular layer without any issue as long as we keep the contract and the interface the same as before. As we will see next, we can actually replace tuple by function to support rational number. This is the second implementation of rational number. We use lambda to represent numerators and denominator. Here is how it looks like. From math import GCD. GCD is needed to compute the greatest common divisor of n and d as g. Then the rational number that you make is actually a lambda function that looks like this. And then you're supposed to supply x to get the numerator here when x is true, or to get the denominator here when x is false. So the numerat becomes return rational number true. Demorat becomes return rat false. If you pass through to the number, you will get the n value, which is the numerator. If you pass false to it, you will get the d value, which is the denominator. And then to check for is it a rational number, you check that rat is indeed a function with this command, is instance. This is the equivalence of the type to check for function. And the numerator is indeed an integer. The denominator is indeed an integer. So this completes the definitions of our new rational number implementation. So what we have done is to replace the lowest level with function and updated our make rat, numer, demo is rat to use functions, while the rest of the layers with no change. At this point, we should note that Python is not really a right language that can protect barrier. Even though conceptually we would prefer this layer, equal rat, add rat, subtract, etc. to access to only this layer, but Python doesn't forbid cross-layer access. That means equal rat, add rat, etc. could actually use function if you insist. You will see that other object-oriented language has this protection done more properly. Now that we are dealing with compound data, the notion of equality needs to be clarified. There are two possibilities of equality. One, equivalence. Two, identity. For equivalence, it means that the two objects have the same content, even if they are not the same object. In Python, we use equal to test for this. On the other hand, for identity, it means it has to be that they are the same object. That is, they are actually referring to the same memory in the computer. In Python, we use is to test for this. When two objects are equivalent, it does not mean that they are identity. When they are identity, means that they are actually equivalent. So we have identity implies equivalence. So here are some examples to show you. A is 1, B is 2. So when you take x equal to the tuple A, comma B, you have this box and pointer picture. X is pointing to a tuple where first item is A, the second item is B. Y is another tuple, A, comma B looks like the same as X, but actually they are not because they are actually two copies now. One tuple here and another tuple here. So when you check X is Y, this returns false because X and Y are not identity. But if you check X, is it the same content as Y? Yes, they do. X is a tuple 1, 2, Y is a tuple 1, 2, so you get true. When you have Z equal to X, which you're creating a new variable Z, which is pointing to the same as X, then Z is X. Yes, this is true because X and Z are pointing to the same memory location in the computer. But if you check Z is Y, no, Z is and Y are referring to the different places. But if you check Z is the same as Y in terms of content, yes, indeed they are. So this shows that the difference between is and equal. It is for identity, equal is for equivalence. Here are a few more examples to see. A tuple, apple 1, 2, 3. Is it equivalent to apple 1, 2, 3? Of course, this is true. Apple 1, 2, 3. Is it an identity to apple 1, 2, 3? Yes, this is true. Is apple 1, 2, 3 equivalent to apple? Oh, here is a tuple 1, 2, and 3. So of course this is not the same. False. If you set A as a tuple of apple 1, 2, 3, is A equivalent to apple 1, 2, 3? Yes. The apple's content is indeed this. So this is true. What about A identity to apple 1, 2, 3? Well, this is no, because A is an object stored somewhere Apple123 is a tuple that also stored somewhere, but they are not necessarily the same as where A is stored. So this is false. A is equivalent to Apple1 or bracket 2, 3. So this bracket is redundant. So indeed, this is the same as Apple123. So yes, A is equivalent to this. A equivalent to Apple1, 2 comma. This is a tuple. So this is different from this. So A's content is different from this now. So this is false. There is a word of caution on the use of is for number comparisons. 3 is 3. Yes, this is true. 3.000 is 3. Well, unfortunately, this is false. To sum up this video, you have seen the compiled data and the different notions of equality. Compiled data help us to reason at a higher level, and you can use it to build complex number set, etc. And we can choose between different implementation as long as we keep the contract, the interface, the same. Abstraction barriers separate usage of compiled data from its implementation. You should use mainly functions at the interfaces, even though Python doesn't enforce it.